All right, well, hey everybody. My lapel mic, I think, is broken, so I have a little mic on my headphone here that I'm going to use that instead, which is why I looks like it's casual day in terms of the lectures here. Hopefully, you watched part one of friction. I'm going to continue talking about friction, and especially we're going to talk about sort of cases in which you're not dealing with flat surfaces, instead you're dealing with tilted surfaces. Is what we're going to talk about today. Um, so to summarize the last lecture, there's different types of friction, and we talked about kinetic and static friction. I hope later we'll be able to talk about air friction, which is also called air drag. Um, as we talked about there, the air friction depends on the velocity. The faster you're going, the larger the force, but that's not true of these two types of friction. So for these two types of friction, it's just proportional to um, the weight, and there's some sort of coefficient in there. But there's no explicit dependence on velocity. So no matter how quickly you slide things across the floor, so if you have a house like mine that has hardwood floors, or the kitchen maybe has linoleum or something, and you're sliding things across the floor, well, the faster you slide it, that does not increase the force. The force is still just the coefficient times the normal force. There are situations in which the normal force is equal to the weight. So as I'm standing here in front of you, if you could see my feet, I'm not accelerating upward or downwards, and so I have my weight, which is mostly my belly, pushing down, but the floor is pushing up on my feet. And so for me, standing here in front of you, the normal force is equal to the weight. But there's lots of situations in which it's not equal to the weight, and I tried to give you a list of those. So like C-clamps, the harder those things clamp down, the more the normal force, right? And so the normal force doesn't necessarily have anything to do with the weight. And the whole reason you want to clamp things down like that is to make sure that there's lots of friction, to hold it down nice and tight when you're sawing something or gluing something together, whatever you're doing with that C-clamp. One example of the normal force not equaling the weight is when I jump up and down here, right? And so when I'm pushing against the floor to go up, the normal force is more than the weight. And so if I was standing on a scale and I could look at the number on that scale, it would give me more than my weight would typically be, because I'm pushing on the floor is pushing up at me, and the scale is going to register that. And then as I'm sort of leaving the ground, the normal force is going to be less than the weight, because the floor doesn't have to push me up as hard if I'm, rising in the air. And eventually, when I'm like my feet are above the ground, the normal force will be zero, because the floor doesn't have to push up on me at all. So there's lots of situations in which the normal force is not equal to the weight. And so this is all good therapy for when you get to exam problems and homework problems in which the normal force, it's very tempting to assume that this friction is coefficient times the weight, but again, that's only in the case where you're not accelerating up or down, and it's on a flat surface. We're going to talk more about this today, actually, and we're going to discover that when you're on tilted surfaces, that is yet another example. There's another example of when the normal force is not equal to the weight. I think I talked about this for a while. All right. So we're going to talk about what's called the Trendelenburg position, which is kind of a tongue-tie thing to say. My understanding is that they do not actually do this in hospitals anymore, but in cases of loss of blood, they might want to try to get more blood going to your head, and so they might tilt you backwards, so you don't lose consciousness, things like that. Again, I'm told that this is not what they actually do now, but the basic idea of it is there's a lot of good physics in it. And so you're working in a hospital, and you want to make sure that this patient does not slide off the table. Maybe not necessarily for their well-being, but to avoid lawsuits is generally what you're trying to do in a hospital. So we want to figure out what's the largest angle that we can put this, because let's say that you want to tilt it back as far as you can to try to retain as much blood as you can. But assuming that the coefficient of static friction is 0.8, how far can you tilt the thing back? And so this is the problem that we're going to break down over the next 10 or 15 slides, actually. So what we can do is we can do a force diagram. Now, In some places, you'll hear force diagrams referred to as free body diagrams. These are two different names for the same thing. So, for example, on Essential Skills, they would say free body diagram, whereas I would say force diagram. I like saying force diagrams because it reiterates the reality that the only thing that should be on a force diagram is the forces. Whereas if you call it a free body diagram, that reiterates the reality that the only thing should be on it is free bodies? What does that even mean? I don't know. Anyway, force diagram. The only thing should be on it is forces. So here's a force. There's the weight of the person. So we're going to sort of think as the weight of the person sort of concentrated at the middle. We're almost going to think about it as like a block that's sort of like sitting on this incline and tilted, which I know is a little bit weird, but that's the simplest way of thinking about this situation. So again, force diagram, the weight is pointing down, but there's other forces too. So there's a normal force pointing not exactly up, it's at sort of an angle, right? Because the bed is at an angle. And then there's another important force, which is the friction. The static friction is the thing that's preventing the patient from sliding down the bed. So these are the three forces in this problem. And we want all these forces to be balanced so the patient doesn't slide off. Because if it's unbalanced, then the patient will probably slide down. So we've got a coordinate system here. We can think about these things. There's actually two different coordinate systems that we could potentially use. And what I'm going to do is I'm going to do the problem both ways. And so I'm calling this the untilted coordinate system, and this is a tilted coordinate system. And you can do it either way you want, but I'm going to show you how to do it the two different ways. So in my class, there's only two movies that you're required to watch. It's the original Matrix, and so Neo is choosing between the blue pill and the red pill, and the point of this picture is that it makes a big difference which one of these coordinate systems that you choose. The other movie you have to watch is Star Wars. I've already had Jedi references. I feel like that's pretty reasonable, right? All right. So whenever you have a physics problem, a good question to ask is what are the x forces and what are the y forces? And so each one of these things potentially has some sort of y component force. Here we're going to use the untilted coordinate system. And so I can kind of draw it out like this. You can see the bed has sort of an angle to the x-axis here. And so we have this angle theta there. What we're going to do is we're going to draw these forces on this thing in an effort to try to figure out what the y components are. So it's going to look like that, right? Now, let's see. So I think this equation is going to, there we go. So this is expanded out now. Now the easy part about this is the weight, right? So the weight is mg, and that part's easy because the weight is parallel to the y-axis here, and so there's no trig that we have to do to figure out what the y component of the weight is. The y component of the weight is the weight because there is no x component of the weight, right? So the trickier parts are what is the y component. And when I say y component, I'm saying like there's some vertical component of both the static friction and the normal force. And so we know it's going to be related to the magnitude of those things, right? So the magnitude of the normal force, the magnitude of the static friction, and then there's going to be some trig function there that's related to this angle. Thankfully, there's only one angle in this question, so we only have to worry about one theta. There's no theta 1, theta 2. This is either a sine, cosine, or tangent, and this is either a sine, cosine, or tangent. All right, so let's try to figure out what these trig functions are. I can't remember, but in a minute we're going to talk about whether this acceleration is 0 or non-zero. So let's think about that for a second. Should the acceleration be 0 or non-zero? Specifically a sub y in the y direction. Well, our goal is to prevent this patient from sliding down the table. Okay, so ideally the acceleration is going to be 0 in that case, right? So we can scratch that out. So that part's easy. Later we'll ask the same question in the x direction, by the way. All right, so now we've got to figure out what these trig functions are. So what we're going to do is we're going to break these things down into two little triangles. So let's take the normal force. So remember from the vectors lecture, all vectors are secretly triangles. And so there's an x component of this thing and a y component of this thing. Hopefully you can convince yourself that this this angle here is theta, right? So the way I would think about it is, let me all right. So this is theta, right? So that, and then if I rotate my fingers exactly by that much in theta, then I've made the angle theta here. That's kind of the way I think about it. Sorry, it's hard to do that with my green screen. Maybe I could do it like this. So my hand is like this, and then I rotate it exactly theta. Well, then this would better be theta right there. I think that works a little bit better. All right. If you really wanted to, you could say, all right, well, this is 90 degrees, and so this is 90 minus theta, and this is 90 degrees, so this is, you know, and then this is also 90, so this would have to be 90 minus theta, and then get theta. Anyway, one way or another, you figure out that that's theta. And now you want to know what the y component is here, right? Because that's what we're doing. So this is really the y component of the normal force, so n sub y. And so if this is the magnitude, you know, it's going to be adjacent over hypotenuse is SOHCAHTOA. There's the CAH is cosine. So it's going to be a cosine, right? And now we've got to figure out this one. Static friction, so we can do the same sort of a thing. So there's our angle. This one is maybe a little bit easier because you just sort of say, all right, well, there's an x component, there's a y component. And we want to know the y component. So that is opposite over hypotenuse should be a sine function. So that means that sy should be fs sine theta. So that's how we get the sine there. So the essential skills can kind of help going over these trig things, but I'll try to walk you guys through them as well. All right, so that's the y. That's all the y component forces. So we don't really know what the normal force is. We don't really know what the static friction is. I think we do know what the weight is, but right now all we know is that these things have to add up to 0. Now the x component forces, again, it's the same forces here. It's just now we're going to think about the x components. The easy part of that is the weight. The weight does not have any x component, so we don't even need to include that. But there is potentially an x component to the friction and an x component to the normal force, so we can put down our triangles again and try to figure out what that is. Try to figure out what these trig functions are. Before we do that, you know, let's think about this acceleration. Is it near 0 or non-zero? Well, we don't want the patient to accelerate in the y direction. Ideally, the patient is also not accelerating in the x direction either. We want the patient to have 0 acceleration in as many coordinate systems as possible. So it would be good if this was also 0. Okay? And so now let's try to figure out what these trig functions are. So again, this is the x component of the normal force. So like this, we figured out that that was the angle last time. Now instead of figuring out this component, we need to figure out what this component is. Okay? And so that's going to be opposite over hypotenuse. Opposite over hypotenuse, SOHCAHTOA is sine. And so this is going to be a sine function, like so. And then we can do the same thing with the static friction, and except now we want the x component. This is adjacent over hypotenuse, and SOHCAHTOA, that's going to be cosine. All right. So now we're in a position to try to figure out what the normal force is. I think that's what the actual challenge of all this was, trying to figure out what the normal force is. Well, actually, the challenge of it was figuring out what the angle is. Sorry, excuse me. We're trying to figure out what the angle is, the largest angle that can hold the patient up before they slide down. I guess we don't know what the mass of the patient is. So sometimes in questions, even though it would be nice to know what the mass of these things are, they just don't give you certain information. And so that is a message to you saying that the mass is probably going to cancel out, basically. So let's think about that in just a second. Again, what we're trying to do is figure out what the angle theta is. Now, so it turns out we can figure that angle. It turns out this equation does not matter as much as this one does. And so we can solve for the normal force here. So in other words, we can add fs cosine theta to both sides. like so. And then the static friction is related to the coefficient times the normal force, so you can sub that into there. And then the normal force, so now the normal force is on both sides. We're not really solving for the normal force, we're just sort of taking this equation and seeing what we can cancel. And so the normal force is going to cancel out, we end up with something like this. And you notice that it does not depend on the mass of the patient. Technically the normal force does depend on the mass of the patient, right? The heavier patient, the more force they exert against the bed. But now we have this equation, we can solve for what mu sub s would have to be at this maximum angle. So we can divide both sides by cosine, we get a tangent. Inverse tangent, I told you earlier, their static friction was 0.8. That gives you a theta 39 degrees, which is a pretty big angle. You know, probably don't want to tilt the patient that far back, but it means that you can tilt it fairly far without having to worry about the patient sliding off. Now, one thing I should say here is that in the last lecture, we said that the static friction is less than or equal to mu sub s times n. So why is this not an inequality? Why is this an equal sign? Well, it's because this is the maximum angle. So the maximum angle that we can tilt this thing is also the angle where the static friction force is the maximum. So I probably should have said Fs max and theta max, and then everything would have been equal signs. And if you look on the homework, there's a lot of questions. It's sort of like, what's the maximum this could be? What's the minimum this could be? They're going to be doing a lot of that. Okay, so that's how you would figure this out with the first coordinate system. Let's do it with the tilted coordinate system. So let me just double check that I'm still recording here. Yep. All right. So in the tilted coordinate system now, everything's sort of like, just tilt your head to the side there. So we have to come up with the sum of the x forces here, but where this is the x-axis, not what we had before. And so there's still the three forces there. We've got this angle, which you can tell that this angle is also this angle, is one of the things we know. So now when I put together this equation, it looks a little bit different. And it looks a little bit different because the normal force is parallel to the y-axis, and so the normal force does not show up in the x direction, right? Because the y-axis is parallel to the normal force, so we don't even have to worry about it. A nice thing is that the static friction is parallel to the x-axis, and so there's no trig function there, which is nice. But now the weight, we have to think about, there's some trig function associated with the weight, which is we're going to have to think about how to do. But before we do that, what about this acceleration? The acceleration in the x direction. Is that 0 or non-zero? Well, we want the patient to be at rest in as many coordinate systems as possible, right? And so this is better to be equal to 0. And so that gives us, so that this is the equation that we get for the forces in the x direction. I think in a second, I think we should think about trying to figure out what this cosine. I don't remember if it's cosine or sine or tangent. Let's think about this for a second. All right. So we have a weight. So the weight is pointing down. We got this angle and this angle. And so I can kind of draw it like this. So if I could just figure out what this angle is here, or this angle is here, I could figure out, I should be able to figure out what this trig function is. So one way you could do this would be saying, all right, well, this is theta, and, you know, sorry, then this thing is 90 degrees. So if this is theta, that means this is 90 minus theta. And to get the x direction, that's wx over w, so that would be cosine of 90 minus theta. And that would be correct, so you could say cosine 90 minus theta here. The other way to do it would you say, all right, well, if this is theta, this is 90 minus theta, and then this angle here is 90 degrees, right? I probably should have written that down there. That means that this is theta, sorry, this is 90 minus theta, and then this plus this angle plus this 90 has to add up to 180. So at the end of the day, you can conclude from all of that that this would have to be the angle down here. And so now to figure out, all right, well, I want to know what this is, Wx. Well, this is opposite over hypotenuse would be sine. So that means this whole thing is Wx. So that means that this would be W sine theta. And if you put it into a calculator, cosine of 90 minus theta, that gives you sine theta. So either way you cut it, you end up with something like this. Try to go through that slowly because some people can follow this rather quickly, and some people need a little bit more practice. Okay. So that's a sine function there. Let's think about the forces in the y direction. Same kind of a thing. So the normal force is easy because the normal force is parallel to the y direction. The static friction is easy because the static friction is parallel to the x direction, so there's no y component of it. The weight is still tricky, but we'll talk about that in a second. Now this is all equal to the mass times the acceleration. Whenever you have the sum of the forces, it's always equal to the mass times the acceleration. Even if the thing is not moving, if it's not moving, that just means the acceleration is 0. But if this is always true, all the sum of the forces always equals the mass times the acceleration in either the x or the y direction. So again, we want our patient to be stationary, not accelerating. So that's going to be 0. And then we got to figure out what this trig function is. So instead of figuring out the x component of the weight, we want the y component of the weight. And since this is the angle, adjacent over hypotenuse is cosine. This thing is essentially wy, so that means that this is cosine theta. But by the way, w equals mg. So like maybe I could have written this with a w, but I think you guys can follow that. So now we have two equations. This is what we got earlier, and this is what we got just now. So now we can solve for what this maximum angle is. Hopefully it ends up being the same thing we got before. To do that, you take the first equation and you solve for the normal force. And so you get this for the normal force, which we didn't actually manage to do in the last one. We just sort of skipped over that step because we didn't really need to because the normal force canceled out. But here we have it. And as I was saying earlier, the normal force is not always equal to the weight. Now if you're stationary on a flat surface, well, your theta is 0, cosine of 0 is 1, well then in that case the normal force is equal to the weight. But in general, if you're on some tilted surface, then that is, the normal force is going to be less than mg, right? Because cosine is going to be less than 1. And so, as I was saying earlier, the normal force is not always equal to mg. There's lots of examples where it isn't. But we can use this equation now to figure out what the angle is, because we have the second equation here. So we can take this and basically put it into our equation for the static friction. Static friction is mu sub s times the normal force. Again, the maximum static friction, right? If we're looking for theta max, we want to have the maximum friction, right? Because if theta is more than this, then the friction isn't going to get any higher than that, right? And so we're going to sub this into our equation for static friction like this. Now the mass and the gravity cancels out. And we can divide both sides by cosine, end up getting a tangent. Inverse tan of that is 39 degrees. So we get the same answer no matter which way that we do it. Which, is good. It would be rather weird if we get a different answer for, how much to tilt the patient depending on which math that you used. But let's review what we've done so far. And let's review what the equations look like depending on whether you do coordinate system 1, the untilted, and coordinate system 2, the tilted. So this is the untilted coordinate system, and for my money, the thing is that there's 4 trig functions to worry about. And actually there's a version of this lecture that I made that I screwed up one of the trig functions. I had to redo the whole lecture because I messed it up. So that does not make life any easier. Over here, there's only 2 trig functions to worry about because the static friction was parallel to x, the normal force is parallel to y. It got a little bit tricky with the weight. There's only 2 sources of trickiness, whereas this one there's 4 sources of trickiness. So often in these tilted problems, I would encourage you to use the tilted coordinate system. Usually, it's up to you. You can do it both ways. but the tilted coordinate system is usually better. So choose carefully which, if you take the blue pill or the red pill, because it has a big difference on what follows. Okay. The next thing is things rolling down tilted surfaces. So not just sort of staying stationary, but actually rolling down. Now in this video, I'm not actually going to show you. I'm actually going to show you the video of this Stephen Hawking's universe thing, which is just, it's only like 30 seconds or something. A little bit of a vignette on the history of science. But basically, Galileo was the first person to realize that things accelerate according to this 1/2 at squared. And the way that he did it was with this device that had a little bell that would ring as the object kind of rolled down this plane. So that's what the video is about. I'm going to skip that here, but it's fun to take a watch. So again, here is the thing that's sort of rolling down, and Galileo would time these things, and because Galileo's father was actually, they had a very musical family. His father wrote operas in Italy, and so he had very good rhythm. Jazz wasn't invented yet, but he still had very good rhythm. And so he would write down on a musical score when these bells would ring, and he was able to use that to back out exactly how quickly the thing was going as it fell down. Because Galileo didn't have smartphones like we do that can record these experiments and do the little things with the dots. This is the best he could do otherwise, and that's how he managed to figure it out. And so the group work today is based on this idea, and I encourage you to, when you're doing this problem, to use a tilted coordinate system. The main reason being is that the acceleration then is only in the x direction, the tilted x direction, right? Otherwise, if you kept the coordinate system sort of, like this, if you kept the coordinate system like this, well then there's a component of the acceleration in the x direction that's positive. There's a component of the acceleration in the y direction that's negative. It just makes it harder to analyze. So that's the group work. There's a force diagram there. Now, in the first part of the problem, there is no friction, so the thing just kind of rolls down. And then at the end of the worksheet, it says, okay, go ahead and add friction to it. And the goal is to see how many seconds it takes for this thing to slide down the incline, and to see how much that changes if you add friction to it. Okay, so that's the group work. So huddle up with your Zoom breakout rooms and work on that and submit it to Carmen.